we are going to see what happens if you are drawing two dependent samples. Then what will happen to the sampling distribution of the difference of the sample means. Now, see, in real life, we may not always come across independent samples, right? Because the samples on the observations that you draw are more or less likely to be dependent on each other. For instance, if you consider the output of a machine and you note down what is the output of the machine before a maintenance is done, and after that maintenance is done, what will be the output. If you compare them, so these are basically dependent samples. Or you can consider in marketing research, suppose they launch an advertising campaign and they want to compare the sales before the launch of that advertising campaign and after that. Likewise, so these are certain situations in which you come across these dependent samples. So we want to see now how the sampling distribution would vary. So far we have focused on independent samples. So now we will focus on the dependent sample. So the first result in this criteria is when the standard deviation is known to us. Okay, so in this case, what happens is that sigma d, which is the population standard deviation, is known. And what is this d suffix? Let us try to see. What it says over here is, if you have xi's and yi's, these are normally distributed, and xi's or yi are dependent. Okay, then so you have xi's, you have yi's, then you can calculate di's. Di's will be basically your xi minus yi. So the difference between these two, if suppose it is the cholesterol level, you want to see what is the impact of the new drug that has been introduced. So suppose it is for checking the cholesterol level. So in that case, before the new drug is introduced and after that, you can measure the cholesterol levels. So suppose this is before the drug is administered and xi's, and yi's are after the drug is administered. So in such cases, they are dependent. Now we will observe, we will note down what is the difference in these values. Once you get these values, you can obtain the mean of this d bar. So d bar would be nothing but summation di, the normal formula, divided by the total number of observations, right? If mean is this is the mean that is given to us, and sigma d, basically this is the population standard deviation of the pairwise difference. So this is for the population one, and it is known to us. Then in this case, we can see that, so the statistic over here is going to follow your normal 0, 1. So let us see why this is happening. Since your xi's and yi's are normally distributed, okay, this linear combination again would also be a normal random variable. So these basically di's are now independent normal random variables with mean equal to and standard deviation sigma. Because initially you had a dependent sample xi yi. Now by taking the corresponding differences, you have made and transformed the dependent sample into a single independent sample or single sample basically. And we have seen earlier in the last week also that if you draw a single sample from a population where the standard deviation is known to us, in that case we have seen that, if you can recall, the sample mean follows normal to mean mu and variance sigma square by n. And if we standardize it, it becomes x bar minus b sigma y root n follows normal 0, 1. Now what is happening is that instead of mu, you have d over here. Instead of sigma, you have sigma suffix d. So we are using this d notation to denote that basically that we are talking about the differences of these. Okay? This di's. And instead of x bar, you have over here, this is d. Okay? So now, which is the same logic. Now you have here di's on a single sample that is coming from normal population. Mean is given, variance is given. So you can simply use this result which we have already obtained, that x bar minus mu sigma by root n follows 1. So instead of x bar, you will use d bar minus mu d. Sigma d by then follows normal distribution with parameters 0 and 1. So it is very easy to see that we have basically transformed your dependent sample into a independent. Likewise, the other case can be when you have this population standard deviation is unknown to. In this, again, if you recall from the last week, what we had was that if it is unknown, then you no longer have your standard normal or the normal distribution, but rather you have a p distribution. Okay, so whenever sigma is unknown, p distribution comes into picture. And you replace the sigma unknown by the corresponding standard deviation. Same thing as we have done last week. Here also, it is saying that if it is unknown, so you have xi's, you have yi's, you know you can calculate with the corresponding differences, pairwise difference. Okay, n would be there. Now you can calculate, ud is given to you, but this is not given to you. Right? So that is why sigma d is unknown, so you estimate it using the sample standard deviation, and the moment we replace sigma d by sample standard deviation, this one, then the distribution becomes t with n minus 1 degrees of freedom. Okay, so it comes from there straight in a straightforward manner. And here also you can see that the proof also is very simple. It's on the same lines as we have done just now, so I am just showing it to you over here. So as we have seen, xi's and yi's are normal random variables. So di, which is the difference between these two, is also a normal random variable. Now again, these are your independent normal random variables. Mean is the population mean, and here you have the sample standard deviation. So we know that t basically, which is your x, instead of, so originally what it is, x bar minus mu s by root n. It will follow t distribution with n minus 1 degree of freedom. So instead of x bar, you would have d bar minus, instead of mu, you would have mu d. S will be replaced by sd divided by root n. This would be following t distribution with n minus 1 degrees of freedom. And this is what your result said. Okay. So now let us see an example to understand that. Suppose here what you are given is, you have a group of 10 male participants in a dietary intervention, and the plan was designed based to assess its impact on their weight, and the weights are given. So before diet and after diet weights are given to you, right? And it is on the same set of 10 individuals. Okay, so they are dependent. Okay, so these are xi's. So this is basically your xi's, x1, x2, x10, and this is your yi. So if you have to deal with this by looking at the data, you can immediately identify that this is a dependent data set. So you would no longer be working and using the original result that we had. That if you have a two sample problem, then how to just use the first A result that we had, right? Let's sigma 1 square and s2 square, you can find out. But in this case, what happens is that, first of all, you would note down what are the corresponding differences, di's. You can rather denote it by capital Di also, so it is no issue. You will note down the corresponding differences. Then you would note down, you will find out its sample mean and the corresponding standard deviation. And suppose if it is given that mu d is 0, then you can calculate the t statistic as this. Note that here I am just finding out the statistic. I am not using it for hypothesis testing because those will be covered in the later weeks of this course. As of now, we have learned about only the sampling distribution. So our focus in all these problems is to reach to a point where the sample statistic can be found out. We know the distribution of that. We know the sampling distribution of each of these in different situations, and that is the objective of this week. Okay. From next week, we will see how to do estimation and other stuff. Since here we are dealing with SD, so basically you can see that here we are using, so here I said, so instead A, if it is known, if the sigma is known to you, Otherwise, you would use the other one which is unknown, right? Or the pooled standard deviation. Now we have seen about the difference of the sample means, and now we are going to talk about the ratio of sample variances. If you recall, whenever we are finding out the distribution of the variances, we learned the result that n-1 times s square by sigma square follows chi-square distribution with n-1 degrees of freedom. So it means when we are talking about the ratio of the sample variance, then also chi-square distribution would come into picture, right? And that is why we have another distribution which is known as F distribution. So let us see what is it. The F distribution says that if you have x and y following chi-square random variables, so let us see if x follows chi-square distribution with m degrees of freedom and y is another chi-square distribution with n degrees of freedom, then if you have in the numerator x divided by its corresponding degrees of freedom and y divided by its corresponding degree of freedom, then it will no longer follow your chi-square distribution, rather this would follow F distribution with parameters, or you can say the degrees of freedom m and n. So first degree of freedom is coming from this side and the second degree of freedom is coming from the denominator. Okay, so this also, since it is based upon your chi-square distribution, so it also takes value from 0 to infinity. So it's something like this, and unlike t or z which are more symmetrical, okay, so normal, standard normal, and these are more symmetrical, but rather chi-square or f, these are in this form. Okay, so this is about your F distribution. So we will make use of this F distribution in finding this next result. The theorem says that when random samples of size n1 and n2 are independently drawn from two normally distributed populations such that their variances are same, this ratio over here, it will follow F distribution. It will follow F distribution with n1 minus 1 and n2 minus 1 degrees of freedom. Right? So by the definition, if you see, it means that this n1 minus 1 degrees of freedom is coming from the numerator and this one is coming from the denominator term. Right? So here we can get an F distribution if we rearrange the terms in such a way that a numerator also has a chi-square random variable with n1 minus degrees of freedom, and denominator would also be chi-square if it is with n2 minus 1. Then only this quantity is going to follow F distribution with these degrees of freedom. Right? So let us just focus on this F that is given to us. So to prove this, here you can see that we are just taking this s1 square over s2 square. Since we want to make it as a chi-square, and we know that n1 minus 1 s square by sigma square will be chi-square. So basically we try to incorporate these n1 minus 1 sigma square for the first one, right? So we have written in this way, we have multiplied and divided it. Again, for the second one, we need n2 minus 1 and sigma square. So we have multiplied and divided over here. And this term, we can see that these all will cancel out. So it will not affect the original term that we had. Okay. Now by just rearranging the terms, you can see that here in this one, if you see the numerator, how we are getting this. So we have just rearranged the terms. So n1 minus 1 times s1 square divided by sigma square, and this term will come. Likewise, here you have this. Now if u is following basically your chi-square with n1 minus 1 degrees of freedom, and v is following chi-square with n2 minus 1 degrees of freedom, then basically you have this, and this distribution, you can see that it will be following F distribution with n1 minus 1 degrees of freedom and n2 minus 1 degrees of freedom. Okay. So the proofs are simple. You have to keep the basic idea in mind that how do you obtain such distributions, right? If you know that it is going to be related to chi-square, so for that you need to also have the knowledge about this one, right? What happens in the original population when we have a single sample. Okay, so that is why we basically learn about a single sample problem and a two sample problem, because if you are dealing with these two, you can easily generalize them over more number of samples. Okay, and then there is no difficulty understanding them because it is a simple generalization and extension of the original format. So everywhere like this, you will be using the original concepts that you have studied in these 2 weeks. Okay. So for this, let us consider this example over here. Suppose you want to compare the variance of two different brands of tennis ball. So brand A and brand B is there. You select 10 tennis balls from brand A and 12 from B. And their sample variances are given to you as S1 square and S2 square. Okay. Now in this case, let us see how you can calculate your F statistic. So here it is easy to see. Suppose S1 square and S2 square is already given to you. N1 is 10 and N2 is 12. Right? So we know that S1 square over S2 square, this is your F statistic. It follows F distribution with N1 minus 1 degrees and N2 minus 1. Right? So S1 square over S2 square, this would be some value. Suppose this is F1 is this thing. Okay. So this one would be 3.6 by 2. You will solve this and its distribution, you will compare it with N1 minus 1, so 9 and 11 degrees of freedom. Okay. So this is about this distribution. We know that immediately it will be following this distribution. And when we go to the testing and estimation part, then we will see that basically we compare this value, the one that you obtain over here, with the tabulated value and compare the results. Okay? Or you can use the p-value method to whether see that there is a difference in these two brands of tennis balls or not. So we will look into it in detail later on also. You see that how this distribution over here looks like. If you are sampling from normal populations, if you are taking both the samples are coming from the first one, X1, X2, Xn, this is also come normal, and Y1, Y2, Yn, this is also normally distributed, and the sizes, sample sizes are same, then you see that as this blue curve corresponds to S1 square over S2 square. Okay, so this blue is corresponding to sample size 5, and then if you increase the sample size to 20 and 100, this is how your skewness is decreasing as the sample size is decreasing. Okay, this is regarding when you are taking samples from normal populations. There might be situations where you are sampling from non-normal populations. Suppose you have taken a sample from uniform distribution, right? You can see that here, in this case, again, if you plot S1 square over S2 square, then the initial histograms might be like this, right? So it is skewed. And as you increase the sample size, this, when you are plotting this, the sample distribution of S1 square over S2 square, you will see that it will become more and more similar, right? It will start becoming like this. So different situations will be there, but as the key idea is that when we increase the sample size, then the sample distribution of the ratio of sample variances would approach your normal distribution. Next, we come to the sampling distribution of the difference of two proportions. So last week we studied about single sample problem where we focused on real single proportion, right? Sample proportion found out, and we denoted sample proportion by P hat, where P hat came out as X by N, and X we said that is same as binomial distribution parameters N, right? If you remember this, where X we said that X is those individuals, N is the total number of individuals, and X are those individuals who have that characteristic. So basically, it acts as a binomial random variable with parameters N. And if you want to study this, it's equivalent to studying this binomial distribution. And we found that it can be approximated by a normal distribution provided NP is greater than or equal to 10 and N1 minus P is also greater than 1. So this we have seen in the last class. So if we see for this one, there you have difference of the proportion. So let us see what is the result in this case. The result says that suppose you have two samples of sizes N1 and N2 which are coming from normal populations with proportions P1 and P2 respectively, then P1 hat minus P2 hat. Okay, this is approximately normally distributed with this mean and this standard error. And this result would hold true if each of these are greater than 10. Okay, so here if you see, so P1 hat will be basically x1 by n1. Okay, similarly P2 hat will be x2 by n2. And what is this x1? X1 would be binomial with n1 and P1 probability, and x2 would be again binomial n2 P2. Right? So P1 hat and P2 hat we know only. And we have seen that it is approximately normally distributed. So we are just going to use that same thing over here. Since x1 and x2 both are these, the P1 hat is this. This is approximately normally distributed, so mean is same. P1, and this is the standard, or you can say this is basically a variance, right? Because expectation of P1 hat, if you find out, this one would be expectation of x1 by n, since x1 is binomial, this would be n2 by p, with basically these two, right? Similarly, if you have to find variance of P1 hat, this one would be P1, because we are dealing with the first one. Variance of this one would be 1 over n square, variance of x1. And we have seen that it will be n cube, so n and cancel out, so you will be left with P1, 1 minus P1, that is P1 divided by 1. Right, so this thing we obtained it last time also, and this is the other one. When two are normally distributed and you take a linear combination of them, they will also be approximately normally distributed with mean as, if you recall from the first one, that is mu1 minus mu2, and the other one will be sigma 1 square by n1 plus sigma 2 square by n2. So now we come to this example. It says that suppose you assume that 5% of the medicines made by drug manufacturing A exhibit a specific side effect, while 4% of that from B display the same side effect. You randomly select 150 samples from this, and both companies' total is 2000 medicines. From that, you just pick 150 randomly. What's the probability that the proportion of medicines with this side effect from drug manufacturer B exceeds that of A? What is the proportion? Let us see. This is the proportion corresponding to first one, and this one is corresponding to the second one. Right? N1 and N2, this is same. Right? This is N. Okay. Now you see that this is also satisfying the criteria that N1, P1, or you can say A, and the other one N2, P2. Okay. So these are same. You can N1 and N2, you can write NA and NB also for elimination, because they are ultimately same also. This is just suffix are used just to make you understand that it is denoting which particular term over here. It depends upon your feasibility and your ease with which you can work. So N1, P1 you can suppose consider, we are more used to that. Just write it. So N1 P1, N2 P2, and likewise N1 1 minus P1, and N2 1 minus P2. See, this criteria is satisfied. All are greater than 10. All are greater than 10. So we can say that we can use the standardize it. We subtract PA minus PB from here and divide by the standard error. So standard error is this that we have just now found out. This is P1 into 1 minus P1 divided by N1. Similarly, P2 into 1 minus P2 divided by 2. You can just cross check if it comes out as 0.024, and when you substitute the values over here, you get the probability response. Okay, so this is the probability that the proportion of medicines with this side effect from drug manufacturer B exceeds that of B. Okay, so with this we basically complete this concept of sample distribution. In the next lecture, we will see how we implement these topics in Python on that. So basically, what we will do is that we will first see how these distributions that we have studied, like P distribution, chi-square, and F distribution, we will visualize them in Python, how do we write the code for them, and we will, in this case, we will see how these examples basically we can solve using Python. Because we have already seen that given a data set, how you can solve it. But suppose you have this much information, precise information is given to you, then how do you write code for that in Python? So we will see that in the next few lectures, and then we will move on to our next week, that is